introduction. I'm talking about the pattern formation, self-organized pattern formation of chemotactic bacteria. I'm working on fluid dynamic studies usually, but this subject is not fluid, but complicated flow behaviors created by small creatures, bacteria. This is the contents of my talk. So in this talk, I mainly talked about two parts. First part is concerned with the development of new simulation method for chemotactic bacteria. And second part is the application to the pattern formation dynamics of chemotactic bacteria. So it is well known that chemotactic bacteria such as Escherichia coli, E. coli, they create very large-scale corrective motions and create patterns. And this picture shows the pattern formation of E. coli in Petri dish. Here they change for example, the concentration of oxygen or concentration of food, chemical cues of bacteria, and they create various type of patterns. Can you see the picture? Maybe, okay. So, and this is another result of corrective motion bacteria. They show that bacteria create the traveling pulse in microchannel. This pulse was moving with a constant velocity. And this is another example of swarm band formation of marine bacteria. Marine bacteria can move much faster than the enteric, and they create some swarm band around the food bead. So this, so my target is this kind of large-scale corrective motion of corrective behavior of bacteria. And this corrective behavior can be characterized aggregation, traveling waves, and swarm, So and these corrective behaviors, all these corrective behaviors stems from rather simple individual motions, which is called lung and tumbler motion. So it is also well known that, for example, E. coli create lung continue lands and tumblers. And when the E. coli rotate their flagella in counterclockwise direction, these flagellas create bundles, and they get thrust and lands just straightly. And occasionally, they unbundle the flagellas and change their directions. So just bacteria continuously reorient by lands and tumblers. But in the run mode, bacteria also sense the chemical concentrations in the environment and change their run lengths depending on the the change of chemical concentration along their pathway. And this is called chemotaxis. So here I just show the schematic of chemotaxis. S is concentration chemical attractant of bacteria. Now when the bacteria moving toward the low chemical concentration region, this direction, they often create tumblers, and they make run length shorter. On the other hand, if the bacteria are moving toward rich chemical concentration region, they make run lengths longer. As a result of these individual motions, the bacteria collectively migrate toward the rich chemical regions. And how they change their run lengths according to is depend on the temporal sense along the pathway. So the bacteria sense the change of chemical cues. The temporal change of chemical cues is lower. Then the bacteria immediately, quickly increase the tumbling rate higher, increase the tumbling rate, and change their directions. And otherwise, if the bacteria sense the chemical concentration, the temporal change of chemical concentration is higher, then the bacteria reduce the tumbling rate and make the run length longer. And this chemotactic response is characterized by stiff and bounded response. Here, the stiff means the bacteria quickly responds to the change of chemical concentration. And bounded means the modulation of tumbling frequency is always bounded. So what is the challenge of this this subject is, for me, understanding the multiscale mechanism between the collective phenomena and individual motion. So, for example, how the chemotactic response strategies affect the pattern formation, large-scale pattern formation, and what kind of property of bacteria are important for efficient collective motions, or more basically, how macroscopic models are derived from microscopic or mesoscopic models. And these are my interest of this study. So to understand, in order to study of the multiscale mechanism, I use the kinetic transport theory of bacteria. So if you are familiar with Boltzmann equation for gases, and this equation is a bit similar to the Boltzmann type kinetic transport equation. The left-hand side just describes the lung of bacteria with velocity v. And here F is the density of bacteria with specific velocity v. And this, the kinetic equation describes the change of velocity distribution of bacteria. And left-hand side is describe the change of chemical change of density of bacteria along the pathway with velocity v. And right-hand side describe the tumbling of bacteria. The bacteria change their moving direction by tumblers. And the first term in the left-hand side, right-hand side is called gain term. Because this term describes the change of bacteria with velocity from velocity b prime to b. And this second term is called loss term because this describes the change of velocity from change of velocity from v to any other arbitrary velocity v prime. And importantly, and this and the capital lambda describes the tumbling rate of bacteria. And this tumbling rate depends on the chemical concentrations in the environment. And of course, this tumbling rate depends on the speed, the velocity of bacteria themselves. And how we obtain this chemical concentration? So we solve another equation simultaneously. The chemical concentration field is described by reaction diffusion equation. Here we consider S is the chemical cues created by bacteria themselves. Bacteria create chemical cues to communicate other bacteria around themselves. And ds is just molecular diffusion of chemical cues. And the second term is degeneration of chemical concentration. And this term describes the production of chemical cues produced by bacteria themselves. And also we consider the food nutrient concentration field. And nutrient is consumed by bacteria themselves, and the last term, minus gamma n times rho, describes the consumption of bacteria. So we solve this equation simultaneously. So one of the most important aspects of kinetic transport equation is in the multiscale properties. So we can so we can derive the macroscopic equation from the kinetic transport equation by some mathematical analysis. For example, in the microscopic model, which includes the internal state of bacteria, was proposed by Elvan and Osma in 2004. And this, here they consider the density of bacteria with velocity b and with some internal state m. But when the dynamics of internal state is characterized by this time scale TA, this is adaptation time. The bacteria adapt to the outside external chemical concentration field. And TA describes the time scale of adaptation dynamics. But if the adaptation is very fast, then this equation, from this equation, we can derive another type of kinetic transport equation. Here, the internal state is just integrated out. And this model was derived independently by Draco and Schmeitzer, independently from Elvan Osma. And now recently, Pelton, Tang, and Boshure rigorously proved that this model is derived from this microscopic model in the first adaptation limit. And when we consider that here the K is important parameter to connect the macroscopic continuum equation. The K describes the tumbling frequency or run length of bacteria compared to the reference length. So small k means the sequential tumbling, continuous tumbling. In the limit of sequential tumbling, the bacterial motion looks like continuous. And then we can derive the continuum equation, which is a well-known Keller-Segal type equation, is this equation, from this equation. Here, the velocity b is also integrated out. And u is the drift velocity of the collective motion of bacteria. And this drift velocity depends on the chemical spatial gradient of chemical cues. And this is the important aspect of kinetic transport equation. The multiscale aspect is important. And this is the reason that I use the kinetic transport equation to understand the multiscale mechanism of in collective motion of bacteria. So again, the next, I would talk about the Montezuma simulation based on this kinetic chemotactic model. Here again, I write the basic equation. This is our basic model. Here, here the tumbling rate separated in two parts, and small lambda describe the tumbling rate, but it doesn't. This does not depend on the. It just depends on the pre-tumbling velocity b prime. It does not depend on the velocity after tumbling. And this tumbling rate depends on the chemical concentration field. And K is described. K describes the probability for changing velocity from b prime to b. And lambda times k describe, this is a scattering kernel in this kinetic model. And for lambda, we have three important parameters. Lambda 0 is the mean tumbling frequency. And the chi, we consider two chemical concentrations, S and N. And chi is the modulation amplitude in change of tumbling frequency. And delta describes the stiffness of the response. And in K function, we have variance sigma. Sigma describes the variance of change of moving directions. And the tumbling rate, here the tumbling rate also depends on the material derivative with velocity, with bacterial velocity. Okay, this is material derivative. It's described like this. And we also consider the logarithmic sensing. So the bacteria can sense the chemical concentrations at the usual scale, not at the usual scale, but at the logarithmic scale. We hire this logarithmic sensing in the model. And the Monte Carlo simulation is similar to DSMC simulation, which is one of the most popular simulation technology for gas dynamics, non-equilibrium gas dynamics. So here we divide the spatial domain in lattice systems, small lattice systems, and Monte Carlo particles are distributed according to the velocity distribution function. And chemical concentrations are simultaneously calculated by the finite volume method on this lattice system. So individual processes are described like this. So first, we give the initial position and velocities of each Monte Carlo particles according to the initial velocity distribution function, and move the Monte Carlo particle in time step size, in the time step size delta t, and then count the population density at each lattice site. And with using this population density, we also calculate the chemical Qs by using the finite volume method on that system. And then next stage, I will judge the tumbling with using this tumbling rate. Here we need to calculate the material derivative, but because we use the Monte Carlo simulation, we use the particle-based simulation. This material derivative along the pathway of each Monte Carlo particle is very straightforwardly calculated, just like this. And then we give the new, for the particle which are judged to make tumbles, we give the new velocities according to this probability. And if we consider the division or death of particles or bacteria, we also judge the division or death of particles with some rate. And we just repeat these processes in Monte Carlo simulation. And first, I applied my Monte Carlo simulation to this traveling pulse problems. In these experimental papers, they investigate the individual motion bacteria, and they collect the data of tumbling frequency and the probability of changing directions. So we can use these data in the simulation. We choose these parameters from the data reported in that paper. And this is the geometry of the simulation. We consider the narrow channel. And first, the bacteria is accumulated at one side, this side. And in the channel, the food and nutrient is uniformly filled. As a boundary condition, we consider the mirror boundary, mirror reflection for each Monte Carlo particles. Okay. This is the movie. The bacteria first accumulated. So each particle represents a bacteria. And first bacteria accumulated on this side, but moving out other side collectively. And this inset showed the population density is drawn by black curve, and blue curve showed the nutrient concentration. If the bacteria moved, after the bacteria moved, population density decreases, nutrient density decreases because which is consumed by bacteria. And when the bacteria arrived at other side, opposite side, then just this pulse reflected in other side and reformed the profile, pulse profile. Okay. So in this simulation, we can estimate the traveling speed, 4 micrometer per second. And this traveling speed is very close to the experimental result. And also the profile of population density, profile of pulse, is also similar to this experimental result. And I also checked the my Monte-Carlo simulation can reproduce some theoretical result. Here I compare my Monte-Carlo simulation result with the Keller-Segal equation. And the epsilon, the vanishing limit of epsilon mean the Keller-Segal limit in continuous limit, which is described this black curve. And when we decrease the parameter k, then our Monte-Carlo simulation result converge to becomes close to the continuous limit equation. So this result demonstrates my Monte-Carlo simulation can reproduce the convergence of continuous limit numerically, just numerically. And next part, I show you the pattern formation result. So as I said at the first slide, the bacteria create very beautiful pattern. And these two movies show how bacteria create the patterns. So here, the bacteria accumulated in this bright region, and they extend their habitat, and they expand their population. And after the frontal population passed, they create this kind of stripe pattern in channel. And this is another result in Petri dish. The first bacteria accumulated at the center in the Petri dish. And they also expand their population. And after the frontal population passed, they create a new annulation link. So again, we consider this pattern formation based on the kinetic chemotaxis model. But for this model, we consider the proliferation bacteria, which is written in this term, the last term of this. P is the proliferation rate. And this term considers the proliferation when the density is lower than the saturation density. But when the density close to the saturation density low equal 1, this P has negative value. And we have the saturation at low equal 1. Okay. And we also consider the stiff and bounded response in this equation. And this, okay. And for the chemoattractant concentration is just described this reaction diffusion equation. But here we omit the time evolution because now the time scale is taken by the proliferation time scale, which is very slow. So we can neglect the time evolution term for S because diffusion is much faster. Molecular diffusion is much faster than the proliferation division time scale of bacteria. And we couple this chemoattractant equation and kinetic chemotaxis equation. And now the important parameter related to instability, related to the pattern formation, is the tumbling rate, mean tumbling rate of bacteria, and modulation amplitude, and stiffness of the response, and molecular diffusion coefficient. And if we carry out the linear instability analysis, we can obtain this instability condition. This condition says that the uniform state rho equal S equal 1 is linearly unstable when the stiffness of response, the left-hand side, is sufficiently large. And furthermore, the unstable mode lambda is always bounded, which means so we can expect the Turing-like instability. So linear instability analysis just as usual is usual one. So we consider the perturbation around the uniform state, small perturbation, and we linearize the kinetic chemotactic equation and seek the instability condition where the real part of IgM mode is positive. If we draw the neutral lines for our kinetic instability condition, this is the instability diagram. So each curve is the neutral curve for different value of k. If the stiffness is just above this neutral line, we can expect the pattern, Turing-like pattern formation. But if the stiffness is just below this neutral line, theoretically we cannot know the stability of the uniform state. To check the sharpness of this instability diagram, I carried out a Monte simulation. This is the result of in the one-dimensional lattice system. Here we consider the one-dimensional variation of chemical concentration S, but particles move in three-dimensional. So the left column show the pattern formation. Here, this figure shows the spatio-temporal evolution of population density, and horizontal axis represents the space, and vertical axis represents the time. The first bacteria's population density is uniform, but as time progresses, when the parameter, the stiffness, is just above this neutral line, we can the periodic pattern is spontaneously formed. But if the stiffness is just below this neutral line, we cannot see such periodic pattern. So this result demonstrates the sharpness of our instability condition. Okay, I skip this. And next, I aim to reproduce the pattern formation observed in experimental system. We choose these parameters, and this is the geometry of simulation. We create narrow channel by two parallel plates. At the wall boundary, the chemical concentration, the boundary condition of the chemical concentration is Neumann at the wall. And at the end of channel, we fix the chemical concentrations. And the bacteria is first accumulated in the center of the channel here. And these narrow channels are divided into not 100, 1,000 times 100 lattice systems. And in each lattice system, 1,000 particles include in the uniform state. Okay, this is the result. We can see that bacteria expand their population, and after the population after the front of population passed, we can see the creation of stripe pattern in the channel. Okay, this is a snapshot, sequence of snapshot. So they extend their population, and after the front passed, they create the stripe patterns. Okay. I skip this one also. And next example is another geometry. Here, the boundary conditions are all Dirichlet type. So here, the chemical concentrations are fixed at the boundaries of this square region. And bacteria are first accumulated at the center in this region. And we divide this domain into 500 times 500 lattice systems. And each lattice system, we put 1,000 particles at uniform state. And this is simulation itself. As first bacteria is here, and they expand their population with creating this annulation layer of annulation sequential. Okay, so this is a snapshot. They expand their population outward, and after the front pass, we can see the ring pattern. Here I change the parameters of tumbling rate. When the tumbling rate becomes smaller, aggregation becomes stronger. And then if the tumbling rate is very large, it means the K is very small. The network-like pattern can be seen. But if K is large, which means the tumbling is small, then the aggregation becomes weak. And pattern becomes slightly unclear. Okay, so I would like to summarize my study. So Monte simulation for lung and tumbler chemotactic bacteria was developed based on a kinetic chemotaxis model. And some corrective behaviors of chemotactic bacteria were well reproduced by the Monte simulation. And comparison to the theoretical analysis verified accuracy and validity of our Monte method. And we also found a novel instability mechanism, which is called stiff response induced instability, both theoretically and numerically. And thank you very much for your attention. And I also thank the collaborators. Thank you very much.